Okay, so yesterday we went over latent heats, specifically as part of the heating curve of water, where we saw this graph. Okay, on the y-axis of this graph was temperature in degrees Celsius, and on this graph was energy added in kilojoules. Okay, and so what we saw was that the temperature of, if we start down here, so 0 is right here, and 100 is right there, okay, that when we start out with ice, if we add heat, what happens to the ice? No, it doesn't melt. It warms up first, then it melts. Okay, that's the flat part of the line at 0 degrees Celsius. Okay, so first we warm the ice, then once it gets to 0 degrees Celsius, it will melt, and there will be this period of time where there is water and ice, okay, concurrently in the container. All right, once we get to here, all the ice is gone. Now that the phase change is completed, then the water will begin to heat up. Okay. Then when we get to here at 100 degrees, the water will begin to boil and vaporize. I mean, some of it will probably have vaporized before that, but the bulk of it's going to occur here. Okay, so we've got evaporation going on. So there will be water and water vapor in the container together, okay, at the same time during this phase change. Okay, and then after that, okay, at the end of that phase change, we'll have steam. We continue to add heat, the temperature of the steam will go up. Okay, anywhere where the line is flat, what kind of thermal energy are we changing? Potential. Yeah, we're changing the potential thermal energy whenever we change state. Okay, that's why we use these formulas here. E equals MLF and E equals MLV. All right, so we're in a state change, we're changing the potential thermal energy. In other words, we're changing how far apart the molecules or particles of that material, in this case water, are. Okay, we're going from a solid where they're packed close together, okay, to a liquid where they're further apart. Okay, and then when we go from liquid to gas, they go even further apart. Everybody all right with that? Okay. When we're seeing the line go up, we're changing then the thermal kinetic energy of the object. And what formula do we use for those sections? E equals MC delta T, because that's the one that has temperature change in it. Okay, the thing we have to remember about each part that uses E equals MC delta T is what? Right, we only want to use the temperature change for that section. Okay, remember we don't want to use the whole thing. Okay, and the other thing is? Right, C is different. The specific heat capacity of ice is different from the specific heat capacity of liquid water from steam as well. Okay, so we have to remember that down here, we're using C equals 2.116 joules per gram degree Celsius. Okay, here we're using that C equals 4.2 joules per gram degree Celsius. And up here, C is 2.02 joules per gram degree Celsius, because water's weird and its solid, liquid, and gaseous forms all have different heat capacities. Yes, we're only going to use this curve for water. Yeah. All right. Is that ringing a bell for everybody? Okay. Then I want you to try those three. Okay, so with number one, we're starting with water at 3 degrees Celsius. Okay, so I'm just going to draw a small version of that graph. We're starting right here, and we're going to 115 degrees. Okay, so that means I have to heat the water, evaporate the water, and then heat the steam. Those are my 3 steps in this question. Okay, so in step 1, okay, I'll be using E equals MC delta T, and in this case, that'll be 400 grams times 4.2, because it's liquid water, times 97 degrees Celsius, because I got to go from 3 to 100. All right, so in step 1, okay, we'll have 400 times 4.2 times 97 for 162,960 joules. Okay. In step 2, okay, we are evaporating the water, so that's E equals MLV. That's 400 grams times 2,260 joules per gram. Okay, so that'll give us an energy there. 400 times 2260, 904,000 joules. Okay, and then our last step is that we need to heat the steam by 15 degrees. So that'll be E equals MC delta T, 400 grams times 2.02 joules per gram degree Celsius times 15 degrees Celsius. Okay, so 12,120 joules. Okay, then we add those three up. So we've got our 162,960 plus 904,000 plus 12,120, 107,070, sorry, 1,079,080 joules. It's the C for steam. Yeah, got it off my chart. On the test, it'll be on the front page or wherever the other data stuff is. Yep. Okay, so on number 2, we're looking for how much energy would be required to warm 1.5 kilograms of ice from minus 17 into steam at 100 degrees Celsius. So this is a 5-stepper, right? Yep, because we're starting at ice, right? At minus 17. Sorry, 4 steps, only at 100. Sorry, 4 steps. Yeah, sorry, 4 steps. Okay, so we have to heat the ice, melt the ice, heat the water, evaporate the water, 4 steps. Okay, so in step 1, that's an E equals MC delta T problem because we're changing the temperature. So that'll be 1,500 grams times 2.116 times 17 degrees. Okay, so 1,500 times 2.116 times 17 gives us 53,958 joules. Okay, step 2, got to melt the ice. E equals MLF. All right, so that'll be 1,500 times 333. Okay, so that'll be 499,500 joules. Sorry, this should be 1,500 times 333. Okay, step 3. We have to heat the water. So that's E equals MC delta T. 1,500 grams times 4.2 joules per gram degree Celsius times 100 degrees Celsius. All right, 630,000 joules. All right, and then our last step, we have to evaporate the water. So E equals MLV. So 1,500 grams times 2,260 grams, all right, joules per gram, sorry. Whoops. I should probably just add another 0 onto that. Okay, so 3,390,000. Okay, add all those up, you get 4,573,458 joules. Okay. All right. Okay. Good there, guys? Right, those were just specific heat capacity. Right, they're just E equals MC delta T problems. Okay, you'll only be dealing with water if there's a state change. Okay, in any other time it'll just be like, you know, you put on a ring that's made out of this metal and 400 joules of energy are lost by your hand. What's the temperature of the ring or something like that, right? It would be, yeah, it would just be a 1-step kind of thing. No, I said that yesterday. Okay, you do not. They will be. They're on. You have a sheet in your digital notes package, and it'll be on the exam. Okay. It would depend on how many digits you kept. But yeah, if I was only keeping 2, it would be 4.6. Don't bother putting in scientific notation. I'm going to want to see the whole thing. All right. Any other questions there? Okay. Oh, sorry, Haley. Yep. Yeah, we can go over next. Okay, so how many joules are released this time? So now we're actually going backwards. Not that that really changes anything. No, I didn't have you do that one. There's like 7 questions. I just didn't show them all. All right, so we're starting with steam at 135, and we're cooling to water at 12. Okay, so that's how many steps? 3. I have to cool the steam to 100. Then it will condense, and then I will cool the water down. Okay, so that's 1, 2, 3 steps. All right, so in step 1, okay, in step 1, I'm just cooling, so I'm changing temperature, so that's E equals mc delta T, so that's 250 grams times 2.02 because it's steam times 35 degrees because I'm only cooling it from 135 to 100. Okay, so that's the first one. So 250 times 2.02 times 35. Okay, 17,675. All right, so there's my joules for step 1. Okay, in step 2, I have to condense the water. Okay, so that's going to be E equals MLV. That'll be 250 times 2,260 joules. That's 565,000, right? I think. Okay. And then in step 3, I just have to cool the water down. Okay, so that'll be an E equals mc delta T problem. 250 times 4.2 because now it's water. Okay, and I'm changing it down to 12, so that's 88 degrees from 100. All right, so 250 times 4.2 times 88. All right, it's 92,400. Okay, so if I add those together, $675,075 joules. Yeah. Alrighty.